In this video, we're going to be talking about electric potential. Okay, now it is on the board, and here is a problem on the board as well, which we are going to be reviewing after we have talked about electric potential. Now, there are two things that usually go in hand when you talk about potential under electric fields. These include the electric potential energy as well as just electric potential. Now, first things first, we're going to talk about electric potential energy, the formulas and equations as well that we use in solving problems on it, and then we move into electric potential, which we can now attempt this problem from there. Okay. Now, first things first, what is electric potential energy? Now, the electric potential energy U is simply the work done, okay, in moving a unit charge in an electric field, okay. Mathematically, the electric potential energy U is given as the force needed to move it times the distance r. Now, the distance I'm going to be representing as r because from Coulomb's law, we do know that the distance is usually represented as r. Even if I make use of this, doesn't really make any difference. Okay. Now, F for the other hand, but we do know that F from Coulomb's law is k q1 times q2, or could as well as big Q and small q, okay, divided by the square of the distance apart. Now, if I should substitute in this, I'm going to get the electric potential energy as kq times q divided by r squared times r. Now, one r takes out one r, and then we'll be left with what? Electric potential energy equals kq times q divided by r. Now, here is a very useful formula for solving electric potential energy. Now, how about a situation whereby we are having multiple charges in a region? What then is going to happen? Okay, multiple charges in a region, and then we're asked to find the net electric potential energy. Do take note that electric potential energy, of which we know that all energies or work done, they are scalar quantities. We don't have to consider the direction, okay, in which the charge is moving towards, whether towards the left or right, or negative x-axis or positive x-axis. All we simply have to do is take the algebraic sum of the values, okay, of the magnitude. So to get the net electric potential energy for a situation where we are having different charges, okay, we're going to have the net electric potential energy, let's call this QT, that is total electric potential energy, will be equal to the first one, which is KQ, okay, into brackets Q divided by R, okay, that is for the first one, plus Q divided by R. Now I'm going to give these ones a sign, so I'm going to call this Q1 R1, Q2 R2, plus and so on and so forth down to the last charge Qn divided by Rn. Now this is not something you're going to come here. Here is the explanation. If, for example, this is a stationary charge, okay, and then we are moving these different charges, or these other charges, they are placed rather at different distances away from Q, okay. Q1 is placed at the distance of R1 away from big Q, Q2 at the distance of R2, okay, R2 away from what now? Big Q, okay, as well as Qn at the distance of Rn away from what now? Q. So to get the net electric potential energy, we're going to sum the potential energy between Q1 and Q, which is what we're having here, the potential energy between Q and Q2, which is KQ times Q2 over R2, okay, and then for Qn as well. So that is how it is being done. All you have to do is factorize out this KQ, which is the charge we're considering, okay. It will be outside, and then we can now have the other charges inside of the bracket, so it's that easy. Now, electric potential, on the other hand, is quite similar to what we're having here, okay, just a slight difference. You should know that electric potential is defined, electric potential is represented as V, okay, and it is defined as the work done per unit charge in bringing a charge from infinity to a point in an electric field, okay. So when I divide this formula by Q, I get what now? The electric potential, in the sense that V becomes U divided by Q. Now we've already proven that U is KQ times Q over R, right? If I choose to substitute in, I'm going to get K, okay, I'm going to get KQ times Q divided by R, which is for U, times 1 over Q, okay, times 1 over Q. Now Q cancels out Q, and then we're left with electric potential is KQ divided by R, okay. Now this formula is worth noting as well. Formula for calculating electric potential is given as KQ over R. Remember, K has the usual value of 9 times 10 to the power of 9, so most times you will not be given any problems just like this one we're having on the board. Okay, now how about when we're having multiple charges in the system and you're asked to find the net electric potential as well? What are you going to do? Okay, we're simply going to take the algebraic sum, just the same way we attempted this problem by deriving this formula, okay, which is the algebraic sum of each of the electric potential energy in the system. Okay, so we're going to do the same thing, and in this case we're just going to be having V will equal, we know K is a constant, and then in brackets we have the first charge over the distance, okay, so it's certain points, plus the second charge divided by the distance to certain points, plus, okay, we have the last charge divided by the distance. So that is how problems like this are being what now tackled. It is quite easy. Now next what we're going to be doing is attempting this problem on the board, which is 2-point charge Q1 2 microcoulomb, okay, located at point x equal to 0, and Q2 plus 2 microcoulomb, okay, located at x equals 50 centimeter. Find option A, or A rather, the work done by an external force, okay, to bring a charge Q3 from infinity, okay, to a point x equals what now, 100 centimeter. And then the other question says the total potential energy of the system of the three charges. Now let's attempt this problem with what we just derived or explained on the board, and so what we're going to get. Now first things first, we might want to draw a diagram on this problem, okay? This diagram will help depict or visualize what we're having in this system because we are giving coordinates, okay? So what you want to do first is draw a diagram, okay? And the diagram says 2-point charge Q1 2 microcoulomb are located at x equal to 0, that is at the origin, okay? So we're going to have something like this. Let's say this is the origin, which is at x equal to 0. We are having Q1 equals 2 microcoulomb, which is same as 2.0, okay? And the distance says that x is equal to 0. And then the next one, Q2, is placed at a position of 50 centimeters. Now, these 50 centimeters can be converted to meters, okay? 50 centimeters, converting it to meters, we're going to divide by 100, which will give you 0.5 meter, okay? So at the distance of x equals to 0, 0.5 meter should be towards the right because it's positive and greater than 0, okay? So we're going to get somewhere here, we're going to get Q2, which is having a value of 2 microcoulomb, okay? Q2 is having a value of 2 microcoulomb, and the distance is 0.5 meter. Now I think this one is negative, okay? I think there's a mistake in the question. This one should be negative. So we're having minus 2 microcoulomb, and this one is minus 2 microcoulomb, okay? That is the correct question. I made an error while writing to the board, okay? So that is all. And then we've determined the position or the location of Q2, okay, with respect to the origin. Now the question asks us to find the work done by an external force bringing a charge Q2 from infinity to a point 100 centimeter. Now infinity is not a specific distance, but we do know that it is outside the reach of the region of the electric flux of these two charges that is very, very far away at some distance. We do not know which we call infinity, okay? I'm beginning from that infinity to a point which is what now, 100 centimeters, or this one is same as 1 meter, okay? So I'm beginning from a point in infinity down to a point in the electric field which is at a distance of Q3 at a distance of 1 meter, okay, in the electric field. So Q3, which is having a value of 1.5 microcoulombs, okay, 1.5 microcoulombs. So I'm beginning from infinity to a distance which is what now, 1 meter in the what now, electric field, 1 meter from what, the Q1, okay. Now the question now asks us to find the work done by the external force bringing to bring the charge from infinity, but have to find the work done, okay, which is the electric potential energy. Now take note that this work done is same as the electric potential energy, and the electric potential energy was the first thing we talked about, okay. The electric potential energy, we said what now, is the work done, which is what we're looking for in what now, moving a unit electric charge in what now, an electric field, okay. And there's a formula for that as well. We did note that the work done is given as F times R, okay, not just F times R. We also derived the formula which was in form of the superposition of charges, okay. I'll do that again, which is KQ times Q divided by R times R divided by R squared. One takes out one, and I'll be left with U equals to K big Q small q divided by R. Okay, now how are we going to attempt this problem like this using this formula? Here's how it's been done. The question asks us to find the work done, of which you know that's the formula, okay? By the external force to bring a charge Q3 from infinity to this point. Now, here's something you should note about solving problems on electric potential energy or work done, okay? One thing you should take note is that this formula, okay, or this energy rather, is a scalar quantity, so we don't have to consider the direction if the charge is coming from this side or coming from this side or anywhere at all, okay? That's something you should consider. Now, which means we're not going to treat this as a vector, which is not, okay, but rather we're going to treat it as a scalar. That's just by adding the algebraic sum. Take note, charges that are negative will still remain negative, unlike the previous problem we solved on Coulomb's law, whereby you have to take the magnitude of these charges, okay? Because those ones have to do with what now? Vectors. Now, for this one, we're just going to work now. Take the sum of what now? Electric potential energy. Now, we are dealing, in this case, we are dealing with charge Q3. So to find the electric potential energy, it will be the distance between Q1 and Q2 that will be required, okay? And also, we do know that as Q3 is being brought from infinity to 100 centimeter, okay, from this Q1, what will happen is this one is positive, this one is positive. As we are bringing it closer, it's what now? Be repelled by this guy, right? So we know we need more work to add into the system for us what now? Counteract the force that is pushing this Q3 away from what now? Q2. And then it will also be attracted by what now? Q1. So we know in the same situation or scenario, we also need less force because it's what now being attracted by this one. That is why we have to work now. Find the net electric potential energy. And to do that, make use of the formula. We're going to get the net electric potential energy to equal KQ, okay? KQ is a constant. Why is it a constant? We do know that this Q is the charge we are dealing with. That is the one we're bringing from infinity, okay? Hence, Q represents what now? Q3. Now, in brackets, we're going to have the other charges, of which this one is attracting it. Okay, we're going to call this Q1 divided by R1, okay, plus this other charge, which is what now? Q2 divided by what now? R2. So you see, this is similar to the formula I wrote on the board initially. So we're going to get a final value of U. K is having a value of 9 times 10 to the power of 9. Okay, now Q is Q2, which is 1.5. So we're going to have 1.5 in microcoulomb. So we know we have to multiply by 10 to the power of minus 6. Okay, and back here, we're left with Q1. In this case, Q1 is minus 2 microcoulomb, okay? So I'm going to have minus 2 times 10 to the power of minus 6 divided by, what is the distance from Q1 to Q2? Don't use the distance from Q1 to Q2. Most students tend to make mistakes like that, okay? So rather, we're going to make use of the distance between Q1 and what now? Q3, of which the distance is what? 1 meter. So we're going to have divided by 1 plus Q2, which is distance from Q2 to Q3, which are what now? Repelling each other. We're going to get 2 microcoulomb divided by 0.5. So we're going to get 2 times 10 to the power of minus 6, which represents micro, divided by 0.5. Now, if we do this on the calculator, by solving the value of the calculator, we're getting the value of U equals 2.7 times 10 to the power of minus 2. Now we're dealing with work done, so that's joules, okay? So it's in joules or Newton meters, okay? Or Newton meters. This is or, not slash. Or Newton meters, depending on the one giving the option, okay? So having 2.7 times 10 to the power of minus 2 joules or in Newton meters. Now that's the first problem being tackled. Now the next question now asks us to find the total potential energy of the system of the three charges. Now to get the total potential energy, here is how it is being done. The potential energy between these two guys will be calculated and then added to the potential energy between these two guys and then the potential energy between these two guys. So here's what I'm saying. To get the net potential energy, okay? Net potential energy, okay? The net potential energy will be the potential energy between Q1 and Q2, Q3 and Q2, as well as Q1 and Q2, okay? I'm going to write it out. So using the same formula, similarly, I'm going to get K Q1 Q2 divided by what now? R1, which is the distance, plus K Q1 Q3 divided by distance R1 3 plus K Q2 Q3 divided by the distance R2 3. Okay, now that's the formula we're going to make use of. Okay, so we're dealing with the potential energy between these two plus between these two plus between these two. Okay, that's what we're going to do. So to do that, we know K is a constant. We're going to have U total equals K in brackets. Okay, Q1 Q2 divided by R12 plus Q1 Q3 divided by R13 plus Q2 Q3 divided by R23. Okay, that's how it is being done. So to solve that problem, I'm going to do it here. Okay, U total equals K is having a value of 9 times 10 to the power of 9. In brackets, what is Q1? Okay, Q1 has a value of minus 2. Okay, now all of them are in microcoulombs, so I can take 10 to the power of minus 6 outside. It will be easier like that. Okay, and to minimize space as well. So I'm going to have minus 2 times, what is Q2? Q2 is 2. Okay, divided by the distance apart is 0.5. Okay, plus, now Q1 is minus 2 again, and Q3 is 1.5. So you have minus 2 times 1.5. Okay, divided by the distance apart, Q1 and Q3, that's 1. Okay, plus the last value, which is Q2 is 2 and Q3 is 1.5. So we're going to have 2 times 1.5 divided by the distance between Q3 and Q2. Here to here is 0.5, here to here is 1. So subtracting 0.5 from 1, you get what now? Here to here is 0.5. So we're going to have 0.5, okay? And all these will be multiplied by the 10 to the power of minus 6, okay? Multiplying by 10 to the power of minus 6 because they're all in microcoulombs, okay? Now to do that, we're going to make use of our calculator again. This is 9 times 10 to the power of 9. Okay, in bracket is minus 8. Minus, that should be 3. And then 4 times, that should be 6. So we have plus 6. Okay, all multiplied by 10 to the power of minus 6. So I'm getting a value of minus 4.5 times 10 to the power of 4 Newton meters. Okay, now here is the value for the total potential energy in the system, which we're asked to calculate, and I just solved it there. Okay, now this negative sign, what does it tell us? It simply tells us that what could be required, okay, to be added in order for us to push this charge from infinity down to a point of 100 centimeters from discharge Q1 in the electric field. That is what this negative sign simply tells us. So that is how problems like this are being solved. In our next video, we'll be talking about electric potential only, not electric potential energy, okay? Talking about electric potential only, and then we'll be solving a few problems on that as well. Do it to like, share with your friends, okay? And subscribe to the YouTube channel. Also, most importantly, rather, do not forget to click on the notification bell so that when a new video is being uploaded, you'll be one of the first persons that get notified when the video is being uploaded. See you in the next video. Stay tuned.